guys, so in this video I'm going to show you how to convert recurring decimals into fractions. Now from what I've seen so far in the new GCSE, it's very common that you'll get a 3-mark question on these, so 3 out of 80 is 3.75% of your paper, so quite a nice chunk for a cheeky little trick. And we are going to include the little proof that 0.9 recurring does in fact equal 1. I couldn't do a lesson on this and not chuck that in here. So first of all, what is a recurring decimal? A recurring decimal is, or a number that has a recurring decimal in it, is a number that has either a single digit repeating an infinite amount of times, or a pattern that repeats in the decimal place an infinite number of times. So it's a pattern in the decimal place that repeats forever and ever and ever and ever more. So all of these here are examples of recurring decimals. Now we use a little dot over the recurring part of the decimal to represent what keeps repeating. So 0.2 with a dot over it just means 0.22222 forever and ever and ever. Same as 0.7 with a dot over it. If we get 2 digits that repeat, so this bottom left one down here, 0.12, now each digit there has got a dot above it, so that's going 0.12121212 forever and ever and ever. If we have a 3-digit pattern repeating, then we put a dot above the first digit that recurs and above the last digit that recurs. So 0.672 with a dot above the 6 and a dot above the 2 goes 0.672672 forever and ever. 0.78 here, where we've only got a dot above the 8. Now if that happens, that means the 7 isn't recurring, so we get 0.7888 forever. And the same down here with 0.34 recurring. Okay, so let's get to how to turn them into fractions. So as I said before, it's quite a nice cheeky little trick. It's actually probably one of my favourite little things to teach people. Okay, so let's start off with 0.2 recurring. Now usually the convention is to use R as the letter for our recurring decimal, but you can use any letter you want. So we're going to say that R equals 0.2 recurring, and we want to convert that into a fraction. So the first thing that we need to do is multiply R by some multiple of 10. We're only ever multiplying by multiples of 10 when we play this game. So the idea is that we need to clear one lot of the repeating pattern. So if we've only got 1 digit recurring, we just need to multiply by 10. The decimal point will move to the right by 1 place, and because we have an infinite amount of 2's in the 0.2 recurring, we can move 1 2 to the left, and bizarrely we still have the same amount of 2's after the decimal point. Infinity is a strange old beast. So if we multiply by 10, we then get 10R equals 2.2 recurring. Now the point of that is that we now have two numbers, two equations if you like, with the same recurring decimal part. And the point of that is that then we can use subtraction to get rid of the recurring part. So what we do now, we take that multiple, the 10R equals 2.2 recurring, and we take away the original equation, R equals 0.2 recurring, and that gives us 9R equals 2. So we've now completely got rid of the recurring part of our number, and then all that was left to do then is to divide by the 9 to get a single R, and that would tell us that R equals 2/9. Now remember at the start we started off with R equals 0.2 recurring. We've now got R equals 2/9. That tells us 0.2 recurring is equal to 2/9. Job done. Okay, same again with 0.7 recurring. We just multiply both sides by 10. That gives us 10R equals 7.7 recurring. do the subtraction, we'll get 9r equals 7. Again, we've lopped off the recurring part, and then finally divide by the 9, r equals 7/9. So something pretty bizarre happens if we play this with 0.9 recurring. So again, carry on as we just have, multiply by 10, 10r is 9.9 recurring. Do the subtraction and we get 9r is equal to 9. Then if we divide by 9, we get r equals 9 divided by 9, or 1. So that tells us that 0.9 recurring is equal to 1, which people always seem to find quite mind-blowing, myself included. It's because the 9 is repeating infinitely. Say that we had 10 9s after a decimal point, and then that was it. That does not equal 1. Even if we had 1,000 9s after the decimal point, that still does not equal 1. It's only because this 9, this 9 is repeating infinitely that 0.9 recurring does equal 1. So it's quite a strange old thing. Have a little think on it. Okay, what happens if we get 2 recurring digits? It's not really that much trickier. All that we need to do is a slightly bigger multiplication to clear the 2 digits this time instead of the 1 digit. So for one like this, we're going to multiply by 100, which is going to it's going to move the decimal point 2 places to the right. So if we multiply by 100, we get 100r is 25.25 recurring. And then as before, we do the subtraction of the original equation from the multiple of the equation. So 100r take away r will leave us with 99r equals 25. So again, we've lopped off the recurring part. And then finally, just do the division. R is equal to 25 divided by 99. Now you do want to be a little bit aware as to whether you can simplify these fractions at the end. All the ones that we've seen so far, we've not been able to simplify, but they do pop up. Okay, what about a 3-digit recurrer? Again, not much trickier. We just need to do an even bigger multiplication this time to clear the pattern. So we've got 3 digits recurring, so we're going to need to multiply by 1,000 this time. And now that will give us 1,000r equals 123.123 recurring. And then again we do the subtraction, and that leaves us with 999r is equal to 123. Now, if we divide by the 999 here, we get r is equal to 123 divided by 999. And this one can simplify down. There's a common factor of 3 between the top and the bottom. So we divide that away and get 41 over 333. Okay, now it's these sort of questions that seem to pop up, especially in the AQA papers now. These are the 3 mark guys, and these probably are the trickiest variation of the problem. So here we've got r equals 0.12 recurring, so it's not saying 0.121212, it's saying 0.12222222. So there is a little extra step in here. The first thing that we need to do is a multiplication so that we get a number with a purely recurring digit. So here if we multiply 0.12 recurring by 10, the decimal point moves to the right by 1 place and is going to give us 1.2 recurring. Now once we've got a number with a purely recurring decimal, we're in a very similar situation to all the ones that we've done previously. We now just need another number with the exact same recurring decimal. So what we're going to do to 10r equals 1.2 recurring, we're going to multiply both sides of that again by 10, and that's going to give us 100r equals 12.2 recurring. And then we carry on as before. We now do the subtraction between these two equations. So we do 100r take away 10r, we get 90r is equal to 11. So we've got rid of the recurring part again, happy days. Then just divide by the 90 and we get r equals 11 over 90, 11/90. Okay, r equals 0.28 recurring, so the same situation as last time. First thing we need is a number with a purely recurring decimal, so let's multiply by 10. We get 10r is 2.8 recurring. Then if we multiply that by 10 again, 100r is 28.8 recurring. So we've got two numbers with the exact same recurring decimal. Happy days. Do the subtraction, and here we would get 90r equals 26. So if we divide by the 90, we then get r equals 26/90. Now that's got a common factor of 2, and simplifies down to 13/45. Okay, let's have a look at one more. So 0.45 recurring. So we need the number with a purely recurring decimal, so let's multiply by 10. 10r equals 4.5 recurring. Multiply that by 10 again. 100r equals 45.5 recurring. Then let's do the subtraction. 90r is equal to 41. And then divide by the 90. We get r equals 41/90. There we go, guys. Job done. Hope it's useful. Cheers.